Okay, so as I in the last tutorial we discussed the week 4's assignment solutions, and in this tutorial we'll discuss about the solution of week 5's assignment. Now let me just quickly uh, go to the assignment so that I can take a screenshot of the question. Just give me a minute. So this is the first two questions. Let me just also take the screenshot of the other questions and then we'll start solving. There are, I think, 7 questions in this assignment, and as I told you, these assignments are comparatively simpler, much simpler compared to what assignments you were given in the first initial weeks. So this should be pretty simple for you, but yet I'll solve it also by myself, and you can check whether that matches with your solution, and whether you have any doubt or confusion regarding any solution, then that also you can ask me. Okay, so the last three in fact are here. Yeah, so now we have all the questions together, so we can just start solving them one by one. So let me begin. So basically, this is mostly this assignment is about van der Waals gas or real gases, and how the interaction and how the equation of gas etc. is for a van der Waals gas. It is mostly discussed in this week's lecture, and the problems are also based on that, as you can see. And then there are problems related to liquid vapor transitions involving Closhes-Clapeyron equation. Then again, van der Waals gas, about the critical point values. These are very important. These mostly comes in many of the MCQs and even in competitive exams. So basically, you have to know this derivation. Anyway, that is standard derivation. And then Landau diamagnetic susceptibility of, then because you have this theory of Landau diamagnetism in the magnetism part of this lecture, and then mostly questions about magnetism, and then lastly the last question is about Pauli paramagnetism. So these are most of the questions. So the vast topic is basically the van der Waals gas and equations, and all the magnetic properties involving diamagnetism, paramagnetism, etc. Right? So so let us begin with the first question, how to solve it. So let us read the question first. It is asked here that what does the parameter A denote? So the parameter is A, and it is asked in the question that what does the parameter A denote in the van der Waals equation. Now there are 4 options given, and you have to choose the option. So basically in the green here there is already the answer is given, that the answer is average attraction between the molecules. That is, the A parameter in the van der Waals equation actually denotes the average attraction. So this is a single line solution, but let me also explain how this is coming. So first of all, we are talking here about mostly van der Waals gas, right? So, firstly, what are van der Waals gas? Van der Waals gas is something that is not an ideal gas. So, we are familiar with the ideal gas, which is the ideal scenario when we describe gases and its properties. But in reality, it does not. It does not always deal with it do not always deal with the ideal gases. It is mostly real gas, which are non-ideal in scenario. So those real gases actually are also known as van der Waals gas and they have a different equation of state, right? Because you know that for ideal gas, you have some assumption of ideal gas, that to for a gas to be an ideal gas there are certain assumptions that are already made to actually simplify the scenario. And the ideal gases equation of state, if you want to write that, I know you remember that the equation of state of an ideal gas is very simple. This is just P into V is equal to some NKBT or NKT, where P is the pressure of the gas, V is the volume, N is the number of particles, Kb is the Boltzmann constant, and T is the temperature. But these ideal gases have some must have some idealistic assumption, as I said, because the name itself suggests that it is an ideal gas, so it only represents a gas in an ideal scenario, which is not always true in a real case. So let me go to full screen so that, yeah. So as I was saying, that ideal gas must have some idealized assumptions predefined. And as I'm sure you are familiar with the basic assumptions of an ideal gas, but I'd actually like to point out that what is the most basic assumption that is actually done in case of identifying a gas as an ideal gas is that uh, the gas molecules are like non-interacting hard spheres. So you can look this up in kinetic theory of gases from any book or internet, and you will get the total set of assumptions that are made for a gas to be an ideal gas. But the one I am talking about is that it is already assumed that the ideal gas molecules have no interaction playing in between them. Like these hard spheres. These spheres are like moving randomly in a container in which the gas is kept, let's say, and the only like kind of interaction that is happening in this case will be the interaction of the gas molecules when they are colliding with the walls of the container. Like that is the only kind of interaction that is assumed. But in between the gas molecules, it is assumed in the idealistic case that the molecules themselves are not interacting with each other in any form. Like they are not repelling each other or attracting each other. They are just moving randomly due to thermal motion, let's say, and they are just colliding with the walls of the container, and that is the only kind of interactive force that is going on in this process. So only interaction is between gas molecules and the walls of the container. Okay. So, or in other words, the molecules are not interacting with each other. So this is an assumption. Obviously, this is not true in a practical case. It is not possible that the gas molecules, they are just moving in proximity to each other and not having any interaction in between themselves. So this is just an assumption that is followed to declare that the gas is ideal gas. So that's why it is an idealistic assumption to make the things less complicated. And the second and crucial assumption that was followed is that the molecules are so small, like obviously the gas molecules will be very small, but in ideal gas assumption it is assumed that the molecules are so small that like in comparison with the total volume of the container in which the gas is placed, the gas molecules have almost negligible volume, as if they do not occupy a significant volume of the whole container, and that's why the total volume that is coming actually from the gas molecule that are moving in the container, that is negligible. So only we focus about the total volume of the container, let's say, in which the molecule gas molecules are placed, but we do not take into account the molecule, because each of the molecule can have individual volume, right? But in ideal gas assumption, it is assumed that the volume of each molecule is very negligible and very small. That's why we do not need to consider that. So the second assumption is that the gas molecules are so tiny compared to the total volume of the container in which the gas is kept, that one can neglect the volume occupied by the molecules. So obviously again this is an idealistic scenario, because in real case obviously however small the gas molecules are, they will have a finite volume which will not, which should not be ignored or neglected like that. But of course in ideal gas scenario we are taking this assumption for an ideal and less complicated formulation of the whole thing. So these are the two assumptions, and based on these two assumptions, when we actually talk about real gases, like in practical case how the real gases should behave, their behavior will be different from the behavior that is expected from ideal gases. And the corrections that are made to actually make the equation of state for a real gas to match with the real properties, there are some corrections that are needed to be made on the ideal gas equation of state, which is this one, PV equal to NKBT. This is a very simplistic equation of state, but this is only valid for ideal scenarios where these assumptions are included or assumed. But when in reality we need to make corrections to the ideal gas equation of state, because then the above mentioned assumptions will not be valid. Above mentioned assumptions won't be valid. So that's where we introduce so the corrected equation for real gas scenario which are non-ideal is the van der Waals equation of state. So you know that any equation of state is actually some relation that connects all these properties like pressure, volume and temperature. And just like PV equal to NKBT, that is the equation of state for ideal gas, the van der Waals equation of state, if we just write it straightforward, that is P plus N squared A by V squared V minus NB equal to KBT. Okay, let's say this is equation number 2, or this is, let's say, Roman 2, and the initial one, this is equation number 1, which is for ideal case, and this is for non-ideal or real case, equation number 2. And you can see that pressure is still P and pressure volume is V, that is the pressure of the total system, and volume is a volume of the whole container of the gas. Kb is the Boltzmann constant and T is the temperature of the gas. But now there are obviously some corrections that are that were not present in an ideal scenario, which are these two terms, N square A by V square in pressure term, and Nb, this component, in the volume term. So now we need to ask that why these corrections are coming and what are the physical meaning of these corrections. So obviously first let us deal with this known one, which is this effective volume is now changed from V to V minus NV. So we can say that the effective volume is decreased by the amount of N times B. Now let me mention that here N is the number of molecules in the gas. Obviously, because in ideal gas scenario, you know the equation of state was PV equal to NKBT. There too the N was representing the number of molecules or particles present in the gas, and here also N carries the same meaning. Only there are two new constants which you till do not know about, or you probably know, but I have not really discussed about here. So A and B are the new constant terms that are coming as a correction term. In the van der Waals equation of state. The correction terms that are needed for changing the ideal gases equation of state to van der Waals gas equation of state. And the volume has this correction term involving the factor or parameter B. So what is B? Basically, B is, you can say that B is almost like the effective volume that is actually occupied by each gas molecule that is present in the gas. So you can say that this is the volume correction. Volume correction term coming because in reality each gas molecule occupy some finite volume in the container where the gas is kept. So basically, let's say if there are n number of molecules, then the total volume that will be occupied by n number of molecules will be n times B. So it is like a significant amount of finite volume which is actually coming because of the occupancy of the molecules in the container. So as if the total volume of the container V is not available right now, because let's say you can think of it like previously there was this whole container which has a volume of V, right, which is the total volume of V. Now the gas molecules can exist wherever they can exist randomly inside this container, and the total container volume V will be available whenever a gas molecule wants to move from one place to other. So total available volume will be always V, ideal cases, because in that case a single molecule is not occupying a certain volume. So whenever you are asking for a gas molecule to, let's say, move from one place to other randomly because of thermal motion inside the container, so it will as if see that it has the total volume of the container available to it, right? Because ideally each molecule will see total available volume as V. But real gas, where each molecule has a volume, so let's say one molecule is occupying a volume of let's say omega, right? Omega is the volume taken by a second molecule. So as if you have a first molecule, when you are introducing a single first molecule to the gas in the gas to the container, then the molecule will have the total space available for it to move, for the movement of it. So for the first molecule that you put inside the container, net available volume equal to V. But when there is already a first molecule and it is occupying a omega amount of finite volume inside the container, so when you now introduce a second molecule, when you introduce a second molecule in the container, so you basically now the second molecule is not seeing the whole volume to be available or open to it, right? Because it has now also, it is now also seeing the volume that is taken by the first molecule. So what will be the available volume that is seen, or that is actually accessible to the second molecule, is basically decreased from V. It is V minus omega, obviously, because now the second molecule has also considered or taken into account the volume that is already preoccupied by the first molecule, right? So its available volume will be decreased from V. It will be decreased by the amount omega, which is the volume of the first single molecule, volume taken by the first molecule. So omega is the volume taken by the first molecule, and when you are applying, when you are introducing the second molecule, so it will see that already omega amount of volume is occupied from out of V. So the available volume to the second molecule will be just V minus omega. And similar, in the similar pattern, if you go on and introduce more and more molecules to that container, so for the third molecule, let's say, so the third molecule will see that now there are two more molecules in the container, so its available volume will be decreased by 2 omega. Considering that each of the molecule is occupying omega amount of volume, so two molecules are already preoccupied the space, so that gives 2 omega, and that is the decreased available volume to the third molecule. And you can go on like that, and you can go to up to nth molecule when you introduce to the system, then you will see that the V will be decreased by some let's say n minus 1 omega. And there is actually a calculation that you can actually go through. I think that is given in the lecture or already, or you can go through any book where you can actually go through the calculation how they are deriving that when you go on and introduce one and one molecule at a time, the available volume to the molecules actually keep on decreasing, and finally the net available effective volume that you can say that is there will be not V, but that will be replacing the V in the equation of state by V minus NB. So this decrease in volume is basically, you can now understand that this is coming from the volume that is already occupied by the gas molecules that are present in the container. That's why this V, capital V, is the net volume of the container. And this N is the number of gas molecules, and B is the, let's say it can be effectively the volume of each molecule, volume taken up by each molecule. So NB is the total volume taken up by N molecules. So this is the, B is the effective volume taken up by each molecule. So the net effective volume that is available in the container after all the gas molecules are there will be V minus NV. That's why this correction in the van der Waals equation of state is not V but V minus NV. So this B parameter, you know that already, although this question was not asked really, the question was asked about the parameter of significance of A, but in the process of that, we in the meantime we already discussed about what B actually suggests, physical meaning of B. And once we know that, so we will also discuss about what this other parameter 8 actually physically signifies. So basically you can know that if you simplify the equation of van der Waals equation of state, then you will get that P plus n square A by V squared is equal to just KBT divided by V minus NB. And then if you further simplify, you will get that P equal to KBT by V minus NB minus, sorry, this will be n square A, not A square, n square A by V square. So you can see that, you can say that this is your effective pressure now of the gas molecules, and you can see that the effective pressure is now decreased from KT by V minus NB minus n square A by V square. So this effective term is actually as if reducing the effective pressure of the gas molecules, and I'll tell you why this is reducing that. So basically here we'll have to take into account that in the ideal gas assumption you had assumed that the gas molecules are not in any case interacting with each other, but in real case the gas molecules do interact with each other. They have some attractive force acting between the molecules, and because of that there will be a reduction of pressure. So this goes as if you can think of it like if you keep on decreasing the volume of the container, as if you are shrinking the total system of molecules together. So the gas molecules will tend to come closer to each other as if they are shrinking into one dense formation. So they will come closer to each other, and as soon as they come closer to each other, so whatever weak attractive force that is acting in between them, as you decrease the distance between two molecules, the attractive force will also increase, right? So in ideal case, if there were no attractive force between the gas molecules, so what would happen is that if you keep on decreasing or shrinking the volume, so the volume will, as like in an some point volume will go to zero, tend to zero, but the pressure of the gas or gas molecular system will be diverging, because P and V are inversely proportional to each other. You know that if there is a constant temperature, then P into V is equal to constant. This is the law that you know, that if temperature is constant, then the product of P into V of a gaseous system is constant. So if you shrink the gas system so that you keep on squeezing the molecules closer together, so that as if V is tending to 0, you are already going to a very dense formation. So in that case, the pressure of the system P should be diverging if this is the scenario and temperature is constant, because you have to keep P into V equal to constant. So if you are reducing one quantity to this extent, so the other quantity should have to also like increase to such an amount that the product should be constant. But this actually does not happen when the gas molecules already have some interactive force acting between them. So but this speed does not diverge to infinity, this pressure rise does not happen. Instead it decreases, it actually decreases the pressure, because the molecules attract each other. As they come closer together, the attractive force becomes closer together. One second, someone has second. Okay, so we are discussing already about the first question in the assignment, that what is the parameter A suggesting, what is the physical meaning of the parameter A in van der Waals equation of state. So as I was saying that even if you keep on shrinking and the volume goes to almost 0, but the pressure does not diverge, because now the molecules also in a real or non-idealistic case, the molecules also attract each other. As they are closer together, they have a tendency to attract each other more. So then that attractive force actually reduces the net pressure by certain extent. And that reduction is actually reflected, as you see, in this term n squared A by V squared. So basically the total pressure is actually decreasing by this factor, and that factor is actually related to somewhat the attractive force that is actually acting between the gas molecules, because they are non-ideal or real gas molecules, so they will have a non-negligible attractive force, attractive interactive force acting between them. They are not like non-interacting hard spheres. So basically you can tell that capital N by V is actually number density of molecules in the gas. Number of molecules per unit volume of molecules in the gas. So basically it is as if it is proportional to, so rho equal to N by V. So it is, this reduction factor is proportional to rho squared times A. density squared into A. So A is nothing but a parameter that actually represents or that is related to the attractive interaction that is present there in between the real gas molecules. So this parameter A denotes the attractive interaction present between the gas molecules in real or van der Waals gas, and that leads to a decrease in the net pressure. So you know the answer now, and also know the physical understanding of this answer, that this is the average attraction between the molecules, which is the parameter A that denotes. Okay, so this question is done. Although this was not a solving kind of a mathematical kind of a question, but I thought that it will be helpful if I just describe why this is the physical significance of it. Okay, so if there is no question about question number 1, then we can move on to question number 2 now. Okay. I thought one of you unmuted yourself, so I thought you have some question. But okay. So our second question is about the van der Waals gas with reduced volume 5 by 3 and reduced temperature is 3 by 2. Then we have to find out what is the reduced pressure. Okay, so first of all, to deal with this reduced pressure, volume and temperature, you have to first understand that from where this idea is coming, that what is the actual relation that we are going to use to solve this question. So there is a mathematical formula that is involved here, right, and that we have to use. Let me go to full screen again. Yeah, so we are done with question number 1. This is question number 2. So we have to take the use of a reduced equation of state. Reduced equation of state for van der Waals gases. But what is the reduced equation of state? Basically, this is the equation of state that is actually coming from the actual van der Waals equation of state. That is this one that I wrote down previously. This one. So this is the actual van der Waals equation of state, but in the reduced equation of state, you basically change all the quantities like pressure, volume and temperature to a reduced value, like reduced pressure, reduced temperature and reduced volume. So how they are related is basically you have to take the total pressure P represented as PR into some PC, where P subscript R is your reduced pressure, and this PC is your critical value of pressure. This is your critical pressure. Okay, and also similarly you can write down the other quantities also, like V equal to VR into VC, where VC is the critical volume and VR is your reduced volume, and similarly T is equal to also TR times TC, where TC is the critical temperature of the gas and TR is the reduced temperature. So all the reduced quantities are PR, VR and TR, and you have to write down an equation of state which relates these three quantities, PR, VR and TR relation. So instead of P, V and T, now we have to represent the equation of state for van der Waals gas in terms of PR, VR and TR. So first of all, let me also tell you why we are writing in such a manner is basically because this PC, VC and TC, these critical values of the parameters like pressure, volume and temperature, critical values of a van der Waals gas are standard values. Okay, that is also mentioned in a question next, that you have to calculate what is the critical value, some critical pressure value, I think. So there is a particular value assigned for a critical pressure or critical volume or critical temperature, and those are standard values for any van der Waals gas, and So basically you can take them as a standard constant term, and because they are not changing, so whatever is changing in the variable in this quantity like pressure is some other factor that is relating the total pressure with the critical pressure. Like let's say your gaseous pressure is P, but this P can be a variable, right? Variable quantity. But this PC, that is a critical pressure, that is a constant because that has a standard value. So if your pressure is a variable quantity, but this PC has a standard constant value. So how these two should be related? So because they both are pressure values, so they should be related by another pressure quantity, which is a connecting factor between them. But the difference that all makes is that this factor which relates this critical standard constant value to the net variable pressure value is another variable which is represented as a reduced pressure, because of its formula, because this reduced pressure is nothing but your total pressure divided by your standard critical pressure value. So that is how this idea of reduced quantity is coming, reduced variable. Similarly, you can also think of it in a same manner for the other quantities, where this reduced volume is nothing but the net variable volume divided by your critical volume, which has a constant standard value. And similarly, TR is also T divided by Tc. And because in any case we have to write down the equation of state connecting all these three variables, and these PC, VC and TC are constants. So just like we can write the van der Waals equation of state in P, V and T, similarly we can modify it or represent the equation of state in an equivalent format. Just instead of P, V and T, there will be PR, VR and TR. But that will not change anyhow the physics of the equation of state, because P, V and T are also variables, and PR, VR and TR are also variables. Just we are changing the form in which it is represented, right? So that is how we should proceed, and I will just first show how we are changing the form into reduced equation of state, starting from the actual equation of state, and then I will show you the answer, final solution. So first let us remember what was our, so for this we need to know already the what are the constant values of the critical variables. So this I'll derive to you later, that how we are getting these values, but these are standard values, so you can also remember it that these values are there. So like critical pressure value for an van der Waals gas is A by 27B squared, and Vc is equal to 3 capital N into B, and your Tc is equal to 8A divided by 27B, I think. So you can see that all these critical standard values are represented in terms of the parameter A and B, which were the correction terms for the van der Waals equation of state. Okay, so these are standard values, you can remember them, they'll be useful, and I will also show you in some next question that how to derive and get these values. So anyway, so once we know that, so we know that our actual van der Waals equation of state was P plus N squared A by B squared, then V minus NB equal to KB T. Now we'll replace P as PR into PC. As I said that these can be represented like this. So PR PC, V equal to VR into VC, and T equal to TR into TC. So let us substitute that in our main equation. N squared A, this V will be now VR square into PC squared. Now this V will be now PR into VC minus NB equal to KB TR into TC. So now we'll use the values of the critical parameters. Like PC, we now replace the actual value A by 27B squared plus square A divided by VR square into VC value is 3 and B, so square will be 9 N squared B squared. Then VR into VC is VR into 3 and B minus NB equal to KB TR into TC is 8A by 27B. So now let us cancel out some of the terms that are common. So like N square cancels out, and So whatever is left we can simplify and take common in some terms, like we can take common a by 27 b squared. So the first term is only PR, plus the second term will be, this was initially 9 PR squared b squared. Now because we have taken this constant term out, so to adjust for that we multiply it by the same term. So in this case this will be cancelling out, this cancels out, and this is 927 is 3. And in the second term we also take out this as a common factor is 3 and b, so the first term becomes VR minus, to adjust for this compensation, is NB by 3 NB equal to KB TR into 8A by 27B. So look carefully that now this term becomes 3 9. So this is A in B. So also this B cancels out with B squared, so it is B. So this is just A times N divided by, I think, 9B, then PR plus 3 by VR squared into VR minus this NB and NB cancels out, so it is just 1 by 3. This is equal to KB TR 8A by 27B. You can also see that this A and this A cancels out, B and B also cancels out, this 9 makes it 3. So what is the total thing that you get finally? This is PR plus 3 by PR squared into VR minus 1/3 is equal to 8 by 3 KB into TR. So this is the final form of the equation of state. Also in because mostly in this lecture series KB, the Boltzmann constant, is taken to be 1 for simplicity. So KB is taken as 1. Actual value is not 1, but it is actually ignored. For the simplification of the equation. So you can just ignore that. Okay. So finally this will be your reduced equation of state. Reduced equation of state for your van der Waals gas. This is its equation number 3. So this is your reduced equation of state for van der Waals gas. And why you are calling it reduced equation of state? Because obviously this is represented in terms of all the reduced quantities, like reduced pressure, reduced volume, and reduced temperature, PR, VR, and TR. That's why it is called reduced equation of state. It is actually equivalent to the basic van der Waals equation of state. So do not confuse that this is some other equation, because you yourself saw that how I derived it. So this is basically the same equation, only the form has been changed. So this is equivalent to the actual van der Waals equation of state that was given in equation number 2 above. You can find it out. Equation number 2 was this equation. So these equation and the below lower equation is actually the equivalent to each other. So now let us go to the question that it was asked in the question that your reduced volume VR was given as 5 by 3 and your reduced temperature was also given as I think 3 by 2. And then it is asked to you that what is the reduced pressure value. Now once you know this formula of reduced equation of state, it is very easy for you to actually calculate that. So let us calculate using this formula from equation number 3. You get that now PR plus 3 by VR square, we replace the value of VR as 5 by 3, this whole square, and then VR minus 1/3. So VR value is now 5 by 3 minus 1/3 equal to 8 by 3 into TR. So 8 by 3 into TR value is 3 by 2, that is given in the question, So cancelling out, this is just 4, and this is PR plus 3 into 9 by 25, and this is 3, 5 minus 1 is 4. Okay, so we are basically in the middle of a solution here. We are solving question number 2 from week 5 assignment. So by replacing the value of the reduced volume and temperature, we calculate the value of reduced pressure. So this is 4 by 3 and this is 4. So this 4 and 4 also cancels out. Okay. Right, so this is just PR plus 27 by 25 equal to 3. So you get PR equal to 3 minus 27 by 25, which is 75 minus 27 by 25. So you get your PR equal to 48 by 25. So this is your reduced pressure value that is calculated from the reduced equation of state. I think this was the answer that was given. Let us check. Yeah, this was the answer. Answer is 48 by 25 as accepted answer. So this is question number 2 solved. Solution is option number A. Now so this is done. So let us move on to the next question. Now this next question is about the equation like coexistence of liquid and gaseous phases. We can directly use the Clausius-Clapeyron equation to solve this and get the answer, but I'd like to also give the physical meaning of that. So basically we'll first start with a little bit introduction how this Clausius-Clapeyron equation is actually coming and how this is applicable for this scenario, and then I'll solve how this answer is coming. So the question is that consider a substance that is basically a system where SL by SG is 3 by 2 and VL by VG is 3 by 5. Then which one of the following statement is true? So now you have to understand here that whenever you are asked or you are given a quantity with subscript L, that means this is the quantity or parameter for a liquid state of the matter, and whenever the subscript is G, uh, this whenever the subscript is G, then you know that that is for the gaseous state of matter. Okay, so basically, so this SL and SG, that means that SL is your entropy for the liquid phase of the system, and your SG is the entropy for gaseous phase of the same system. Similarly, you know that VL and VG, what are they? So VL is the volume of the liquid state of the system and VG is the volume of the gaseous state of the system. Volume of the liquid and gas phase of the system. And so basically this is the all the information that is given to you. There is certain ratio that is maintained between SL and SG and certain ratio between VL and VG. Now you have to know what is the relation between the pressure and the temperature for the same substance, because in the options it is given, all the options are in terms of whether the pressure increases or decreases with the increase or decrease in pressure, right? So you have to know from this information that is given to you that what is the relation that actually connects the pressure and temperature for the substance. Okay, so that is actually that actually takes us to our Clausius-Clapeyron equation that we can directly take use of that, but let us like go a little bit backward and try to understand how we are getting this. So this will not be long. So first of all, we can draw the phase diagram. Okay, I am sure all of you are familiar with the phase diagram for simple system between solid, liquid and gaseous phase. So my drawing may not be accurate, but you can also look this up from any book or let's say internet. Just type the phase diagram, P versus T graph for liquid, gas and solid phase, and you will get the actual diagram. So let me just draw very crudely. So this is basically your phase diagram, where this is your triple point. So you can mark it. So always your phase diagram are in terms of P versus T, pressure versus temperature. So you already know from the question that your answer that was asked, that you are supposed to give, is the relation between the pressure and temperature, right? So it is almost like understanding the phase diagram, because phase diagram is nothing but pressure in the y-axis and temperature in the x-axis, and how they actually behave with respect to each other under different phases. So this phase diagram is basically your pressure versus temperature relation and how they behave for a substance. So this is your triple point temperature, which is, let's say, T subscript P, that means the triple point temperature, and on the pressure axis it will be also P subscript P, this is the triple point pressure. And also this one here is your critical point, and also if you mark this one also, you'll get a certain critical point value of the temperature and pressure. So let's say it is Tc. Sorry, this is not properly done. So you have to join the line, straight line. So this can be your Pc, critical point pressure. So now if you now identify the phases, what phase lies where. So this is, here will be lying your solid phase. Okay, this is your solid phase in this territory, and this is your, if I am not wrong, this is your liquid phase. Okay, and here lies your gaseous phase. So basically in the phase diagram, you can see why this is the triple point. You know that triple point is where all the three phases actually coexist, or this is that equilibrium point between all the three phases of matter. That's why it is called the triple point. Like, it is a coexistence of three phases. So here you can see that the solid phase is also there, liquid phase is also there, and gaseous phase is also there. So it is as if the equilibrium common point between all these three phases. So that's why it is called a triple point. But in this question, what is more useful to us is this line that I am highlighting in yellow. I think you can see. So this is our concern, that this line is basically, you can see this is the boundary line between the liquid and gas phases of the substance. So as if this is the common point, or this is the equilibrium existence of the two phases of matter, that is the liquid and the gaseous phase. So along this line, the liquid and gas phase of the substance can coexist in equilibrium. Okay, so the two phases we are concerned about here is only liquid and gas phase. One is identified by the subscript L with the quantities, and the other is identified with the subscript G in the quantities. Now, what is the connecting relation between these two phases here that we can use? So that is a Clausius-Clapeyron equation. And how can we get the equation? First, let us start with a factor called Gibbs free energy. So this is a known factor in thermodynamics. So this is a free energy quantity known as Gibbs free energy, which has a formula like this, that G equal to H minus Ts, where H is the enthalpy, T is the temperature, S is the entropy. So this is a standard thermodynamic relation. I do not need to describe that. And H can be also written as U plus PV. This is also a standard relation already done in initial lectures. You can check that if you have forgotten. So this is U is your internal energy, PV is pressure times volume, and all these things. So this is one relation. So from here you can get that your Ts is nothing but your U plus PV minus the Gibbs free energy, right? This is one thing. And also this is a known standard relation in thermodynamics, is that Ts equal to also can be represented as U plus PV minus mu times N, where mu is the chemical potential, N is the number of particles. This is the chemical potential and N is the number of particles, you know. So basically from these two relations you can see, if you compare, you will see that there is a common connection, that your Gibbs free energy is nothing but mu times N. That the relation is that Gibbs free energy is equal to chemical potential times the number of particles. Okay. So if that is the case, then that is one thing. But then this thermodynamic relation also tells us that if you take a differential of this dg, that what is the small change in dg, it is also known that there is a standard form, that it is equal to minus s dt plus v dp. Okay. So basically this can be written like that. And now if you, let's say, represent small g as capital G divided by N, as if it is the Gibbs free energy divided by the total number of molecules. That means the Gibbs free energy per molecule can be represented as small g. Similarly, if the total entropy is capital S, then if you divide it by the number of molecules, then the entropy per molecule is represented as small s. And similarly can be done with volume also, that the total volume by the total number of particles can be represented here for this case. This is basically represented as your small v. So these are the newly defined quantities. And once that is done, this is taken that your d capital G by N, because N is a constant, so this does not get affected by the differential anyway. So your d small g can be written by d capital G by N. And because N is a constant, so it can just come out directly from the differential, as if this is 1 by N into dg. Okay, so that means that from this it is known that d small g equal to 1 by N into dg. That means it is minus s by N dt plus v by N dp. And you know that how we have represented s by N is basically small s. So this is small s dt and this is small v dp. So what you get is that your dg is represented as minus small s dt plus small v dp. Now do not forget that g is also taken as mu times N. That means g by N is nothing but your chemical potential mu, which is also g small g, because capital G by N is small g. So basically you get that d small g is basically d mu. It is equal to minus small s dt plus small v dp. So you get the differential of the chemical potential. And the main crucial factor here is that when two phases are in equilibrium, so their chemical potential will also maintain a balance. That means if gas and liquid phases coexist in equilibrium, then d mu L equal to d mu G. So their chemical potential will follow a relation such that the change in the chemical potential for the liquid phase, that's infinitesimal change, that is d mu L, will be same as the infinitesimal change in the chemical potential for the gaseous phase, d mu G. So this is the condition of equilibrium between any two phases. For this case, the phases are gas and liquid, so this relation will be valid. And if that is true, then using this relation over here, you get minus small s L dt plus small v L dp equal to minus small s G dt plus small v G dp. Basically, you have used this relation and replaced this in terms of liquid and gas phase. So, for the liquid phase, the S's are given as A subscript L, V subscript L, and for the gaseous phase, they are represented as A subscript G and V subscript G. So, we take things to one side, that is your S. So, this is small s, do not get confused sometimes. So, this is your S by N basically, this is not the capital S. Small s minus small g into dt is equal to VL minus Vg into dp. So now you directly get what is dp by dt. dp by dt is equal to your, this is small s obviously, small s minus small g divided by small v minus small g, small vl minus small vg. So this is known as your, this is a famous equation called Clapeyron's equation. So what this equation tells you, you can know from here that this dp by dt is nothing but the slope of the P versus T graph. That is the slope of any line in the phase diagram, because your phase diagram is itself a P versus T graph. So this is slope of any line in the phase diagram, and that is represented as a difference in entropy between the two phases divided by, so this is not the total entropy, this is total entropy by the total number of molecules. So let me write here that S equal to capital S by capital N, small v is equal to, so these are small letters, small v equal to capital V by capital N, and divided by the difference between the two phases in terms of the reduced volume of V by N in liquid and gas phase, right? So now you can now directly use the formula to get our answer. That what was given is that your values of these ratios were given, that your SL, this is small s, SL minus SG was given in the question as 3 by 2, and your VL by VG in the question was given as 3 by 5, right? So basically let us represent it only in terms of L phase. So SL equal to 3 by 2 into SG and VL equal to 3 by 5 into VG. Now replace this in the main Clapeyron equation, that dp by dt is equal to SL minus SG divided by VL minus VG. So replace this value and this value here. So this is 3 by 2 SG minus SG divided by 3 by 5 VG minus VG. So this is S. If you calculate it, so this is just half SG minus, so this is 3 by 5 minus 1, which is minus 2 by 5 VG, which is basically half into 5 by 2 SG by VG, which is your minus 5 by 4 SG by VG. So this is your dp by dt. Now you do not need to solve any further, you have already gotten your point, which is basically that because this Sg and Vg, these are all positive quantities, entropy and the volume of the gas, these are, take these as positive quantities. So this overall term dp by dt has a negative factor, that makes dp by dt less than 0, because there is a negative sign here coming from the denominator. And if dp by dt is less than 0, then that means that the slope of the line where the liquid and gas phase coexist is actually has a negative slope in the phase diagram. So if that is true, then already it tells you that dp by dt is negative. That means if you decrease the temperature, the pressure will increase, or if you increase the temperature, the pressure will decrease, because it has a negative sign. So if you increase one quantity, the other quantity will decrease, right? It will have a reverse effect like that. So what will be your answer is that this was actually given in the one of the options, which one matches, is that this pressure increases with increase in temperature will not be true. This is wrong, because in that case your dp by dt would have to be positive, but this is not what we have achieved. You have achieved this, that pressure decreases with increase in temperature, because you got dp by dt for this case applying these conditions is less than 0. That means if you increase your temperature, your pressure has to decrease. This is the answer. No change in pressure with change in temperature will not be true, because in that case your dp by dt would have to be 0, but that is also not true. All the statements are false, not true. So your answer is option number B for question number 3. So I hope this is clear, and so we are basically done with 3 questions. We are left with 4 more questions. How much time we have left? Let us see. Yeah, we have still an hour approximately left, so we'll be done by then. Let us start deriving this question number 4. This is the point that I was telling you about just in the last question, last question, that where we express the reduced equation of state for the van der Waals gas, and I use the values of the critical quantities of Pc, Vc and Tc, and I also directly wrote down what are the values, standard constant values of these known quantities, and I told you that there will be a question coming in the next one or two questions after that, where we have to directly calculate these values of the critical quantities. So this is the question you will get to solve. This is asked only the critical point pressure, that means you are only asked about the value of Pc. From looking at the answer, if you remember our quantity value that I used for question number, this question number 2 I had used. So if you directly remember the value, you can just directly know the value and tick the answer number is B. Okay, so these B and D are very close match. Don't get confused and puzzled that there is a squared in the question number, option number D. So this is not true. Our true option is A by 27 B square, which is your PC. So you can directly know the answer and tick it off, but we'll actually solve all the critical parameter values so that there is a solid idea how these critical point parameters are coming and how they are derived. So let us start solving. So this is our question number 4. Question number 4. And we have to get all the critical point quantities. We have to solve them. So first of all, just in the last question, we had drawn the phase diagram for a system, which is P versus T diagram, and we pointed out which is the critical point and where lies the critical point. So I told you that if this is a rough diagram, then this one is the triple point with TP and P, and with this point at the end of this liquid gas coexistence line is called as the critical point. So if you extend this on the t axis, this is your TC, If you extend this axis, this is your BC. Okay, yeah. So now to solve the critical point quantities, we have to use the van der Waals equation of state and some condition on the van der Waals equation of state which will actually give us the exact critical point value. And that condition, I will directly write down the mathematical conditions that are required first, and then I'll describe or explain why this condition is required. So first of all, the van der Waals equation of state that we need to use is this, that P plus L square A by B square B minus in B equal to KT. So yeah, this is equal to KT, and let's say equation number 1 here, and the conditions, so the critical point conditions we have to use, these are very crucial for the solution. Critical point conditions, some boundary condition, some sort of, you can say that the slope of dp dv del p by del v, slope of p versus b graph will be 0, and also the second derivative, that is del 2v by del v2, also will be 0 at critical point. So at the critical point, these boundary conditions have to be maintained, that this first derivative dp by dv will be 0 at this point, and also the second derivative, which is del 2p by del v2, will be 0 at the critical point. So by following that, when you do the mathematics, we'll eventually get the values of PC, VC and TC. So let's say if our critical point value, we denote it by C, let's say C is our critical point, where C has this quantity values as PC, VC and TC. So whenever we are writing C, we assume that it has the quantities valued as PC, VC and TC, right? So now here comes the explanation why we have to use this kind of a condition. What is the physical meaning of it? So this is a mathematical formation that we have to use, but what is the physical meaning behind it? So first of all, you know that what is your P versus V diagram for an ideal gas, right? So P versus V diagram, if you can search in the internet what is the P versus V diagram for an ideal gas, you can get it. You can get a much better diagram, but I'll just roughly draw by hand here. So the diagram goes somewhat like this. Okay. So there is basically some all this then go up like that, and you can connect here this dotted line, you can connect like this touches here, and further above it can continue to move like that, basically like a rectangular hyperbola if you assume. So this is again a rough diagram because I am drawing by hand, so it may not be very accurate, but just get the idea. So all these have some constant temperature values, like let's say this is T1, this is T2, T3, T4, T5. So these are called isotherms because all of these curves are made in P versus V, but they are drawn at a constant temperature. So they are called isotherms for ideal gas. This is, remember, this is for ideal gas, not van der Waals gas. This is ideal gas. And this total regime here that I have marked, and now I am marking it by a dashed line, has a special significance that one second. So yeah, so this is your to the left hand side this is your liquid phase, and on the right hand side this is your gaseous phase. How can you denote that? Because obviously in simple terms you know that gas will have a larger volume than a liquid. So when you are much further in the volume axis, that will be your gaseous phase, and where you are mostly in a high pressure and low volume axis, that part is your liquid phase. So if this is your liquid versus gas phase, and how their pressure versus volume behave in a constant temperature like in an isotherm will have a particular pattern. Like this red dashed regime is the regime where the two phases lie in equilibrium. So this is the equilibrium regime of liquid and gas phase. So for an ideal gas, when it is transforming or making a phase transition from liquid and gas phase, in between there will be a regime where it will have a equilibrium coexistence of the liquid and gas phase, and that regime will have a behavior like this, as if this is a constant line and then again it falls down. Okay, then again as if this goes like that. So at this equilibrium regime, as you move on to higher temperature, so basically in this case you are increasing the temperature as you are going from T1, T2 to T5. So you are basically increasing the temperature of the isotherms, increasing temperature order. So you can observe that as you are increasing the temperature, this flat regime where the equilibrium regime actually lies is actually getting decreased or reduced as you are increasing the temperature. And finally, at this point, this is the termination point where there is absolutely no such regime in between, where the equilibrium regime actually vanishes from the phase, both phases. So there is no equilibrium happening after this one. So this is the critical point. So if you mark this point, this is your critical point, because this is the boundary line. Below this, at all temperatures, you can see there is a equilibrium regime existing between the liquid and gas phase. But when you are crossing this point, then you see there is absolutely no such equilibrium regime. It is basically a simple rectangular hyperbola kind of a isotherm behavior of P versus V, right? So this actually tells you that this critical point has a particular value assigned to it, which is a standard value. So this critical point, you can mark it in the p-axis as Pc. This is the critical point pressure, and on the t-axis, on the v-axis, this is Vc. And the isotherm T4 on which this appears, this critical point appears, has a particular significance, that this is not some ordinary temperature, but this is called as critical point temperature or Tc. So basically you get your quantities, parameters, that you have your critical point pressure Pc, critical point volume Vc, and the temperature at which the isotherm appears is the constant temperature of Tc, which is a critical point temperature. So basically you know now what is the physical significance behind the critical point. And similarly, this is drawn for ideal gas. Similar thing can also be thought of for van der Waals gas. Only the nature of the graph will be a bit different, but the idea of critical point will be just the same. Okay, so let us draw it by ourselves. Again, this is a P versus V diagram that I am going to draw. Okay, but because this is a van der Waals gas, now let's say this is for ideal gas, right? And then one that we are drawing right now, this is a non-ideal or van der Waals gas. Now the behavior will be a bit different, that the curves will go like this. Instead of a flat regime and then going down, it will have a curvature like this. And as you move to increasing temperature, this curvature will be reducing, and finally at temperature it will be vanished totally. And once you cross that temperature, this will be a completely smooth isotherm without any curvature like that. So you can again join a line to identify this regime where this is happening. How we can do that? First of all, you can observe that this is kind of a behavior where if you draw a line, this is not a flat regime as before, like you saw for this ideal gas. So you can join a flat line, try to join a flat line like before, and you will see that instead of a flat line, now you have curvatures like such that you have now three crossing points on that flat line. Like initially you had this flat line, like right, for this ideal gas, but now if you draw imaginary flat line like that, you will see that now the curvature of the isotherm is such that you have now three crossing points on that flat line. So this is a significance that is only valid for van der Waals gas, because you remember that in the van der Waals equation of state you have this v square term as a correction term. So basically this, once it is multiplied with the v term over here, so it will have somewhat a dependence on v cube. Okay, so this equation will have somewhat a v cube dependence. That means a cubic dependence on the volume. So in van der Waals gas, because you have this cubic dependence on the volume, this basically mathematically tells you that that particular quantity has three roots from that equation. So if you kind of like to solve the van der Waals equation of state, because it is in terms of v cube, so we'll have at least three roots for the value of v. Roots means the not square root, it's roots that you, as in you get values, three values of v. So by solving the van der Waals equation of state. So basically because this is cubic in volume, that's why this is just the understanding, not important in this scenario, but just for the sake of it I am telling you that that is why it is having this kind of a behavior. But now you can identify a similar regime as you saw here for the red marked regime, and once you try to mark it, so it is basically goes like this, and then after some point it is just vanishing. Yeah, so you can again, this is the dashed regime, and the idea is similar, that this is your critical point. This is your critical point. These are your isotherm constant temperatures T1, T2, T3 and T4, all are in increasing order of temperature. That means going from T1 to T4 you are increasing the temperature. Okay, and you can mark your other critical parameter values, which is, this is your PC, which is your critical point pressure of the van der Waals gas. This is on the v-axis your Vc, critical point volume of the van der Waals gas, and this temperature at which this appears, T3 in this case, is your Tc. So don't get confused with the indexing T1, T2, T3, T4. These are just random temperatures that I have given. The main point is that below the critical point temperature Tc there is a certain behavior, and above the behavior completely changes. Like in this case, you have on this critical point the quantities are Pc, Vc and Tc. So at T less than Tc you see that there is a curvature like this, so that you have a regime in between. So again this red dashed line is your equilibrium regime between the two phases, liquid and gas. Okay, similarly this part will be your liquid phase, and this part you have your gaseous phase, and this is your equilibrium regime. So at T less than Tg and all the isotherms you have, these are van der Waals gas isotherms, and these are, this left one is for ideal gas isotherm and right one is a van der Waals gas isotherm. And at T less than Tc you will have, all isotherms will have a equilibrium regime between liquid and gas exists, but at T greater than Tc there is no such regime. No such regime is there. So below and above Tc there is a two different kind of behavior. Like above Tc, when this T4 is greater than Tc, and all these T1, T2, these are below Tc. So this both you can see having a different kind of a behavior. And similarly for the ideal gas also, this T4 here is your Tc, so all these T1, T2 and T3 have an equilibrium regime. So these are temperatures less than Tc, and this T5 is your temperature that is greater than Tc. So already you see two different kind of behavior. And why we are writing down that on the critical point this derivative, first derivative and the second order derivative of del p del v and del 2p del v2 equal to 0? Because mathematically you can see that this point, critical point that we have identified, is nothing but the inflection point that you know from mathematics of a graph, that there is some inflection point when there is a certain curvature change of a graph, right? So this is the inflection point of this p versus v graph. So that's what you know, the property of inflection point is that there the slope of the graph will be 0 and the derivative of the slope will also be 0, because since critical point is the inflection point of p versus v graph, and on the inflection point you know the slope is 0. Slope at critical point C we have identified is equal to 0, and also the curvature, that is the derivative of slope, will also be 0. Okay, so now we have justified why we are using these two conditions, del p del v and del 2p del v2 equal to 0. Now we can directly move on to the mathematics solution part. Okay, so for that let us first express p simplified in terms of the other quantities. So from the Van der Waals equation of state, using this equation number 1, you can take out all the other terms on the other side and just write down p simply on the left hand side. So what will it be? It will be p equal to kt by v minus nb minus n square a by p square. This is your p for the Van der Waals gas, and so you have to take the derivative, first derivative. So del p del v is equal to just minus kt divided by v minus nb whole square minus this v square makes it 2 n squared a by v cube. Okay, and also let us because we have to use the condition that at critical point C this quantity will be 0, del p del v will be 0. That means this t and v, all these will be expressed in terms of tc and vc now, because you are sitting at the critical point. So this will give you that your k times tc is vc minus nb whole squared equal to, because the right hand side is 0, so it will be represented as 2 n square a by vc cube. So this is your equation number 2, let's say. And similarly, when you try to take the second derivative, del 2p by del v2, so because we have already taken out del p del v, you can take another time derivative on this term and you will get, so this quantity you have to derivative once more time, take derivative with respect to v. So this is plus 2 kt v minus nb whole cube minus 6 n squared a by p to the power 4. Okay, once again, because you have to apply this condition of inflection point for the critical point, that at critical point this quantity is 0. That means your 2k tc, that means you have to plug in tc and vc in terms of the quantities and equate it to 0. That means your 2k tc by vc minus nb whole cube equal to 6 n squared a by vc whole to the power 4. So this is your equation number 3, right? Alright, so you have to now use the equation number 2 and equation number 3 to solve for tc and vc. So you can simplify very easily that your this quantity ktc by vc minus nb square has a certain value known, so you can just replace this quantity in this term, right? So how to do that? Let us 2 into ktc by vc minus nb whole square. Let us take it out. So there is a cube term, so one more term is left, that is vc minus nb equal to right hand side was 6n squared a by Pc to the power 4. Now using equation number 2, you know that your this quantity is 2n squared a by Pc cube. So you replace it here, 2, this quantity 2n squared a by Pc cube 1 by Pc minus nb equal to 6 squared a by Pc to the power 4. So cancel out terms, n squared a cancels out, this 2 making it 3, Vc cube and Vc to the power 4 making it only Vc. So you get V 2 by Vc minus nb equal to 3 by Vc. Further simplifying, 2 Vc equal to 3 Vc minus 3 nb. So you get Vc equal to 3 nb. So just match it with the value I had written earlier, that the critical point volume is actually 3 nb. This I used in question number 3, I guess. No, question number 2. So you can check that this value is your critical point volume already expressed. Now by knowing the value of Vc, you can now just directly use the equation number 2 and get the value of Tc by putting the value of Vc. So you get your Tc is now, sorry, your KTC was something, so basically express your TC is now 2 n squared a by Pc cube into Pc minus nb whole square by k. Now I already told you the Boltzmann constant for simplicity in this lecture has been mostly used as 1. So you ignore the value of kb and deal with the other terms. So now you plug in the value of Vc, which is 3 nb. So Vc cube is 27 n cube b cube into 3 nb minus nb is 2 nb. So 2 nb whole square means 4 n squared b squared. So this is basically 4 into 2, 8 n squared. This is n to the power 4 by n cube. That means n. Sorry, there is a problem. Vc minus nd. I am missing out on some n factor, I think. Let us, yeah, this KTC by Vc minus nb whole square equal to this. So if you write down just TC equal to 2n squared a by Vc cube. Now ignore k, value keep as 1. This is Vc minus nb whole square. So 2n square a by Vc cube into Vc minus nb whole square. So Vc minus 2n square. N squared a by 27 n cube b cube into 4 n squared b squared. I think some n factor is, let us see, 8. This is n because n cube is here, n a divided by this b square and b is b, 27b. It has to have some n factor missing. 27rb. Let me check if I am getting this wrong. Say 2n squared. 2n squared a by Vc cube to Vc by. Okay, I think there was one. Yeah. So the equations, I think e by v square and t. Pv equal to nkt. Oh, sorry, I think in the main equation of state I had one factor term missing out. So because in the main ideal gas equation of state you have Pv equal to nkt, right? So when you are modifying it for a van der Waals gas, you have to also keep check that there is a n factor on the right hand side. So that will be same. So there will be a nkt terms instead of kt. So basically in all the previous equations, the equation was right. Instead that there is a n factor missing on the right hand side term. So I actually got confused because sometimes people tend to write this v minus nb. People take this n factor as common. So there is an equivalent form that people can use, standard textbooks can use, that you take out this n factor common so that you have this v by n minus b here, and also similarly from here the cancels, the factors are taken out as common, and because of that this n on the right hand side cancels out with the n on the left hand side. But in our scenario, because we are just directly changing P to P plus n square A by V squared as an effective pressure and effective volume as P minus NB, but we totally ignored this nkt part, because in ideal gas scenario also for n number of molecules you have to write nkt. Unless your n value is already 1, you have to write this nkt. So similarly for van der Waals equation also you have to write nkt on the right hand side, because the right hand side is not changing. Whatever is modified is on the correction is made on the pressure and the volume. So that's why. So all the earlier equation does not change because of this constant n factor that I missed out. But basically because this overall does not change the solution that we had made earlier, that does not make any difference. Like, let us check whether it will change anything. Yeah, this TC value I had written, so this has to be used. And okay, so basically that's why I was thinking there is a missing n factor that should be there. And if, sorry, this is nkt on the right hand side, so basically in all these terms you have a n present. So like here you have an n present in VCQ, right? So this TC equal to, this is in VCQ. Just take the, just make the correction. Sorry, I missed out on one factor, but just make the correction with me and tell me if I am missing out anything again. So this is again in left, this is in, so this factor will have in, this will have a in left here, and this will be like in VC. Sorry, there is some problem. Yeah. So basically when I am equating these two parts, so both of them has a n factor on both sides, right? So like here we have n kt ktc, so when you are replacing it, we have to replace by this, that your last equation, what was it, is that your take this n to the numerator, so this n ktc divided by this whole term is your 2n square a by vck. So when you replace this in this term, so there is no n. In the next line that have to be a correction. This is n. So when you replace, this is just n ktc into vc by nb square, is the whole term is now 2n square a divided by this thing. So there is no additional n, because this is just an adjustment. In both sides, both equations you have n, so both of them cancelled out and adjust each other. There is no n here. So up to this the solution remains the same. Then after that the change is made when there is a additional n term on the denominator, because I missed out one n on the right hand side. This n and n cancels out, so this is just 8a by 27b. So this is your TC value, that critical temperature value in terms of A and B is 8a by 27b. So this is again a standard value. Now the question you are asked is that what is PC? So for that you have to directly use the expression of P here and plug in the values of T as TC and V as PC. So let us write that down. PC is your in TC divided by VC minus NB. minus n square a divided by bc square. I hope this is correct. And so we plug in the value of dc as 8a by 27b divided by 3nb minus nb is just 2nb minus n squared a by 2nb whole squared is 4 n square b square. So you take this in and it cancels out. This 2 and 8 makes it 4. 4a by 27b squared minus this n square and n square is cancelled out. This is a by 4b squared. So sorry, this is 3nb, right? So this is not 4n square b square, this is 9n square b square. So this makes it 27b squared, then 4a minus 3a, which is just your a by 27b square. So this is your answer, that the critical point pressure is a by 27b squared. Already for that we already derived the value of Tc as 8a by 27b and your Vc is 3nb. So this derivation is done. We are done with question number 4. The answer is a by 27b square as I got. Okay. Now question number 5 is about Landau's diamagnetic susceptibility. This is a very short question, it will not take much time. Then question number 6 is a conceptual question, and then question number 7 is another derivation. So let us get done with it quickly. Question number 5 is about Landau's diamagnetic susceptibility and Helmholtz free energy. So we are asked about the relation between them, right? So Landau's diamagnetic susceptibility is represented as chi subscript m. It is a diamagnetic susceptibility, and Helmholtz free energy is represented by this capital F. Okay, and these are the some relations, and we have to get what is the correct relation. So first of all, this question number 5. This is about Landau's diamagnetism. So you know the diamagnetism is when you apply a field and all the magnetic moments actually move in the anti-parallel, in the opposite direction of the field direction, as if they are repelling the field. And in case of diamagnetism, you also know that you do not need to have a uncompensated magnetic moment or spin in the system. This is not dependent on the magnetic moment or spin of the system, but this is an inherent property, magnetic property, that is present in every system, irrespective of whether it has unparalleled or uncompensated spin present or not. And every system has some diamagnetic property inherently present. And the formula and the calculation regarding diamagnetism actually given by Landau gives you some term, and this is actually leading us to the diamagnetic susceptibility of Landau that he calculated. And so basically the idea is that in this case you have to express the free energy potential, which is this, in this case the Helmholtz free energy, in expanded in a series format in terms of the field, that is H. So let's say you apply a very small field, because whenever you are applying a field, the moments are actually moving in the, they are oriented in the anti-parallel direction of the field. So that is about diamagnetism. So you apply a very small field just to make the change. So very small field, as if H is tending to 0. So where H is your applied field. And then how you can represent your free energy, how you can expand it. So your F as a function of H, this is your free energy of the system. This is as written as F0 plus this is your F0. This is like a Taylor series expansion we are doing about H equal to 0. That's H squared by 2 double prime 0, and the higher order terms are neglected because obviously this is a very small field, h tending to 0. So all the higher order terms will have negligible contribution. So you see that this is expanded about 0 field, that is h equal to 0. This is a Taylor series expansion. Okay, and because the higher order terms are ignored because h is tending to 0, the whatever field is applied is very small. Now there is another concept you have to utilize, is that you know that the magnetic moment, this is a standard expression, that your magnetic moment in any system has a relation with the derivative of the free energy with respect to field. This is the Helmholtz free energy, by the way. Standard representation is F, Helmholtz free energy. So you know that the magnetic moment, if this is M is a magnetic moment, then M has a relation connection as del F del H. And you know that the spontaneous magnetization of a system is basically the magnetization that is present in the system even when the applied field is 0. So if your magnetization is capital M, which is magnetic moment per unit volume, this is magnetic moment per volume, this is the magnetization. Because we are saying spontaneous magnetization, so let me write it as M naught. So M naught is the spontaneous magnetization, which is basically the simple magnetization, which is magnetic moment by volume under the condition that h equal to 0. So spontaneous means that you are applying no field, but yet you have some magnetization present in the system. That's why it is a spontaneous magnetization, and this is at h equal to 0, 0 field, and the expression is 1 by v del f del h at h equal to 0. So this is your spontaneous magnetization expression. This involves a derivative of free energy, Helmholtz free energy, with respect to field, because your df in such a magnetic system has a dependence of term like, also there is a minus sign should be there, I think. Yeah, there will be a minus sign. So because this has a dependence on m dh, so I am not writing down the full term, but just like you have df equal to minus s dt minus p dv. This is for a gaseous system where you have pressure and volume as important quantities, but when you are dealing with a magnetic system, you have these extra terms as magnetization and magnetic field. Then df has a dependence on m dh, so that m is related to the derivative of f with respect to h. That's what I have written down, that it is minus 1 by v del f del h at h equal to 0 is the spontaneous magnetization. But for diamagnets, that means it has no spin in the system, right? It has no uncompensated spin. For diamagnetism, electrons spin are not present, or this is basically uncompensated spin. Like we have in case of paramagnetism, you have to have some uncompensated magnetic moment, but for diamagnetism it is assumed, we assume that electrons are as if spinless. So even if they have spin, all of them are compensating each other. So as usual, as if they are spinless. So if they are spinless, that means whenever you are not applying any field, so at h equal to 0, the spontaneous magnetization will be 0, because there will be no spin on the system, right? So that's what makes this minus 1 by v del f del h at h equal to 0 equal to 0. And because v is a finite volume, so v is not any value, 0 or any value. So basically your f prime at h equal to 0 is equal to 0. Why? Because it is a diamagnet, where f prime h is your del f del h. Okay. Now one factor is done. So now we can also further simplify it, because f h equal to f0 plus h f prime 0 plus squared by 2 double prime 0, and other terms are neglected. So take one derivative with respect to h on the left hand side, which makes it f prime h And because f0 is a constant term of free energy at a is equal to 0, so the derivative makes it 0. And this is first derivative makes it f prime 0 is constant. So once you take a derivative with respect to h, it is just f prime 0. And this is again 2h by 2 double prime 0. Now you just now achieve this condition that f prime 0 for diamagnet is 0. So this term is already 0, right? So what you have left is that you have f prime h is equal to h f double prime 0. Now don't forget that your this quantity magnetization has a standard form that is minus 1 by v f prime h, right? This I had written down earlier, that this is minus 1 by v del f del h. So this was spontaneous magnetization, so we had this condition used, h equal to 0, but for simple magnetization it is just 1 by v del f del h at any finite h. So that is the case. Now just replace the value of f prime h from here. So this is minus 1 by v h f double prime 0. So now basically you take h to the other side, so m by h equal to minus 1 by v f double prime 0. And you know that m equal to chi mh, where magnetization and magnetic field are related by the magnetic susceptibility. So in this case, chi m is your diamagnetic susceptibility. So m by h is your diamagnetic susceptibility m, which is nothing but minus f double prime 0 by v. So in other words, you can represent f double prime 0 equal to minus chi m into v. So this is your answer. You can match it here. This answer. This is actually given. So this is done. Now question number 6 is given that materials with spinless charged particles under an external applied magnetic field show which magnetism. So I already told this thing in the earlier question that for diamagnetism only you consider the electrons as spinless. In all other cases you do not take the consideration. So whenever you are assuming the electrons as spinless, that means whatever magnetism is there is an inherent property that is not dependent on the spin. So answer is diamagnetism because it assumes the electrons to be spinless. So this is the answer already. It does not need any further explanation. And finally, we do the final calculation for question number 7.
Ma'am, I have one doubt.
Yeah.
Ma'am, temperature dependence not there, ma'am. In this case, how magnetization when we are talking about?
In which
Do,
question?
no, previously where you derived it. No, I don't. That in that free energy term, we no any temperature dependence. How we are talking about in the magnetization? Lastly, how?
Question number 5, right? You are
Ha ha
asking
ha
that
ha
why
ha
I
ha
did
ha
not
ha ha. Yes,
expand in
yes.
the free energy in terms of
Yes, yes,
temperature.
yes, yes. There.
So basically you will see in like in many systems in Landauer's theory itself, if you read about that in Statmic, you will see that we express the free energy and expand it in terms of that quantity that is dependent, that is the main factor in this case. Like for a magnetic system, you have this magnetic field that is being applied, right? That is taking the things. So we are not right now bothered about the temperature dependence. Of course there has to be a temperature dependence because you know whatever prefactors that are as a coefficient that are present with the terms, like whenever you represent any free energy as some, let's say some first term constant is a, then some b times f prime h into h plus some c times h squared into f double prime h. So all these coefficients or prefactors that are present like this, let's say this in this case your f prime 0 was a, right? So this can have a temperature dependence, or these quantities they can have a temperature dependence, but right now we are not bothered about the temperature dependence of the prefactors. We are only bothered about what is the relation between the susceptibility and the free energy. So in this case the temperature dependence is not useful, but obviously there has to be a temperature dependence that is actually present in these coefficient factors.
Okay, ma'am. Right.
Okay, yeah. So now let us move on to our last question. So it will be a bit of a derivation, and after that we'll be done. So it is asked that what is the effective number of Bohr magnetons at high temperature in a Pauli paramagnet. So and the options are given. So first of all, you know that Bohr magneton is represented as mu b. So this is basically a magnetic moment standard uh, representation. Like if your mu is your basic magnetic moment, then it can be taken as a standard unit of mu b. Like mu b is a constant, it has a standard independent value, and your total magnetic moment, sometimes it is a very standard thing to do in statmic, that your magnetic moment can be represented in terms of mu b. Like say if your mu has certain term, then you can always represent that mu as some factor multiplied by mu b. Okay, as if you are writing this mu as units of mu b, and in that case whatever prefactor is there, whatever coefficient is there, is your mu by mu b. This is your coefficient, and this is basically when you are asked about the effective number of Bohr magnetons. So you are basically asked this similar question, that you have a total magnetic moment which is some constant times your Bohr magneton mu b, and your effective number of Bohr magneton means as if how many number of mu b's are present in the total mu. So for that you have to divide the total mu by your mu b, and the coefficient factor that you get is your effective number of Bohr magnetons. So that is the thing, that is the basic idea we will follow with. And so let us start the derivation. So we'll have to use the quantum theory of paramagnetism for that and get the answer. So to use the, because it is asked for a paramagnetic system, so quantum theory of paramagnetism, we have to get our net magnetic moment, and after that we'll be done. So I'll not go into much details about the total theory because that will make the whole thing very long, but just the basic factors for the derivation is that for quantum theory we have some certain orientations or angle of orientations in which the atomic dipole moments that are present inside the system, that are giving rise to the magnetization, they have some certain orientation with respect to your field direction. As if the orientation angle is theta, then there is a relation that is followed, that cos theta is equal to capital M subscript j divided by total j. This is what we start off with, where this theta is basically coming because in quantum theory you have only certain discrete, this word is very important. In classical theory everything is continuous, all values are allowed, but in quantum theory there are some discrete allowed values. Like in this case you have some certain discrete orientation angles theta of atomic dipole moments with respect to your applied fields direction. Let's say this is your H. Okay, and that what are the discrete values that are allowed is given in terms of this condition, cos theta equal to mj by j, where j is your net angular momentum, quantum number of each atom, which is represented by L plus S. L is the orbital and S is the spin angular momentum quantum number, and J is total sum of L plus S. This is because there is spin orbit coupling present in the system, and your M subscript J is nothing but this is called a magnetic quantum number. Remember, you are dealing with now quantum theory of magnetism. So this magnetic, so all these quantum numbers are coming, and this mj is having 2j plus 1 number of possible values. So these are all standard things, I do not need to explain this, but this mj can take values right from minus j up to plus j in gap of 1. Like mj can start with minus j, then minus j plus 1, then minus j plus 2, and similar to this you can have j minus 2, j minus 1 up to j. So this is a total all possible values of mj that are there, and all this values has a total of 2j plus 1 count. Okay. And when you are asked to take the total magnetization, so magnetization is your capital M, which is you have to take the statistical average of the individual atomic dipole moments. So because you need to take the statistical average of atomic dipole moments. So you know the idea of statistical average. You have to consider what is the, like, first of all let me write down the equation. So this is m equal to n sum over j from minus j to plus j, then m subscript j, g, this is the g factor you know that comes often in the magnetism. Then mu b is your Bohr magneton, then e to the power exponential to of mj g mu b. B is your applied magnetic field, divided by k is your Boltzmann factor to T, temperature, divided by again minus j to plus j summation, then exponential of the same factor. Okay. Because this is a statistical average, so why I am writing it down like this? Because the number of atomic dipoles having mj as a magnetic quantum number is proportional to this Boltzmann factor, e to the power minus, let's say, w by kt. You know that Boltzmann factors are represented like this. The probability or the number of something for the statistical quantity is often represented as a Boltzmann counting factor, e to the power minus w by kt. And in this case your w is the potential energy of the magnetic dipoles, which has the expression as this will be minus mj g mu bb. And why these terms are defined like that, you can just go to any textbook or probably in the lecture, because that is not the main point. I'll just show you the derivation, and these are basically basic expressions that you have to understand why these are coming. You can look it up in quantum theory of magnetism from any standard magnetism textbook. Okay, so this is minus mj g mu b into b. So basically is whenever you are asking for capital M as a statistical average for all the magnetic dipole moments statistical average, so if the individual moments are this, and then you have to take the statistical count as this factor, exponential factor, and then you have to take the summation from all the possible values of mj. That is why you take the summation from minus j to plus j. And because it is a statistical averaging, so obviously we have to have this total count as a summation on the denominator also, and this is multiplied by total capital N, because this whole bracketed term is for individual magnetic moment or individual atomic dipole. And if you have n number of atoms in the system, so this is also not just number of total atoms, this is number of atoms per volume, because you know that magnetization is magnetic moment per volume. So you have to multiply it with the number of magnetic moments, the number of atomic dipoles divided by the volume, and this is for each atomic dipole. This is the bracketed term is your magnetic moment. You multiply it with n and you get the net average magnetization, right? So after you define that, let us for simplicity we denote the term g mu b by kt in the exponential as z to simplify things. Otherwise you have to write down the whole term again and again. So now your m is your n, because g and mu b are constant terms, we take it outside the integration. They do not depend on the the summation, because they do not have any dependence on the summation of minus j to plus j. Only the dependent terms are inside the summation right now, that is mj, then e to the power you have mj times z, because we have identified this quantity as z, divided by the summation is minus j to plus j e to the power mj z. Alright, so now you just have to solve for this summation, so for this bracketed part. So this we can write as b dz of ln minus j2 plus j e to the power mj z. Why? Because very simply, if you take the ln of this quantity and then you take the derivative with respect to z, what you get is that basically 1 by first of all this quantity, and then because in here also you have a sum, in the exponential you have a z factor, so when you take the derivative on this part you have an mj coming out, then to the power mjz, and again this summation. So this is nothing but the same quantity, only represented in a other form for the sake of the calculation. Okay, so in the next line you write down this n g mu b d dz ln. Now this series, this summation, you expand it out. So for the first time it has minus j, so it is minus j into z. So basically this summation is all the possible values of mj. So you have to replace the value of mj as each value of the series sum. So first of all it is minus j, then the second term is like e to the power of minus j minus 1 z. Sorry, this has a plus, or you can write on the other way around also. So we are starting off with minus j, so the next term is minus j minus 1, then all the in between terms, and then we are finishing off with e to the power plus j minus 1 z plus e to the power of jz. Just we have expanded out our series, and now n g mu b. So if you look carefully, you will see that this is a geometric series sum, because you can take 1 e to the power jz as common, so from this side. So let us now write down the series from this side for our sake of simplicity. So this term will be now 1, and the next term will be e to the power of minus z left, and this continued with the last term will be minus jz, means it will be minus 2jz, right? So this we can identify it as a series, geometric series, where the first term of the series is 1 and the multiplicative factor of this series is basically e to the power of minus I think to the power of minus z, yeah, e to the power of minus z. So you know that the geometric series goes like 1 plus r square plus dot dot dot. Let's say there are n number of terms there, so the multiplicative factor is r, that is multiplied in each term. So the summation goes as like 1 minus r to the power n by 1 minus r, where there are total n number of terms and the multiplicative factor is r. So this is a geometric series sum. Similar thing can be done here. Once you have taken out this e to the power jz as common, you see that this is a similar expression. So the series sum will be 1 minus e to the power of minus 2j plus 1 z divided by 1 minus e to the power minus z. Now e to the power minus z is your r, so that has no confusion, and 2j plus 1 in this case is your n. The total number of terms are 2j plus 1, because obviously that is the total count of mj values. So that I have replaced in terms of n in the series sum, and this thing we obtain. So now further simplifying n g mu b d dz of, now we simplify terms, like we adjust a few terms here and there, that so that it becomes j plus half z minus to the power minus j plus half z divided by to the power of z by 2 minus to the power minus z by 2. So this is a very obvious thing, just you have to adjust things a little bit so that you take out 1 e to the power minus z by 2 common. So what happens is that you get this term in the denominator, and similarly you can take out a term in common so that you have now terms looking like this. So basically this you can solve for yourself that this term and this term are equivalent to each other, just the formation has been changed. And once that is done, you get overall structure of the system, where this is a sine hyperbolic function, because this is e to the power x minus e to the power minus x. You know that it is sine hyperbolic j plus half z divided by this is sine hyperbolic z by 2, right? So once that is done, then this thing actually can be further simplified as again this derivation, how this middle part is coming. So basically you can solve it taking the ln and derivative manually, or also you can take use of any software like Mathematica or something like that, and you will actually get this expression. This is also present in standard textbooks, that you will get this expression afterwards, so you can check it for yourself. And it's not very hard to do. In Mathematica it can be done in minutes. So this is cot. So the sine hyperbolic function changes to cot hyperbolic when you have taken the ln and also the derivative like that. So this is the final form that we get. And this total function is actually your Brillouin function. Bj a is your Brillouin function. Okay. And what was your a is basically your a, you have redefined your a. So a is nothing but your j times z. So for sake of simplicity, again you have redefined the term j times z as a, which is nothing but z has also a different value. So the total value of a is g mu b divided by k2. This is your a value. And this is your final average magnetization expression for the applying the quantum theory of paramagnetism. Now we have to, you know that cot hyperbolic x has a form x inverse plus x by 3, this series expansion. So if you simplify it, it is just 1 by x taking in common. This is x squared by 3 plus all the higher order terms. Now in the question it was asked that what is the value, the effective count under the high temperature condition. So you have this condition in mind, that you have to use a high temperature limit on this expression of magnetization. If your temperature is very high, then your a value, which is going as the inverse of temperature, will be going to 0. So t tends to infinity makes a tends to 0, because this is your a value, which has the inverse temperature dependence. So that means in all these factors you see that there is a cot hyperbolic some multiplicative factor into a, and also in this term it has cot hyperbolic a by 2j. So in cot hyperbolic argument you have a, which is going to 0 under high temperature limit. That means cot hyperbolic x, if you take the expansion, you have to use the condition that x is going to 0. In this case a is going to 0. Then you can ignore all the higher order terms. All the higher order terms can be ignored, and you can just write up to up to the second order. Okay. So under this simplification, we now rearrange the terms, that cot hyperbolic a by 2j under this expansion is just 2j by a, this is your 1 by x, 1 plus 1/3 squared by 4j squared. This your x is just a by 2j in this case. And also in the magnetization expression you have another term as called hyperbolic 2j plus 1 by 2j into a, and that is written as 2j by 2j plus 1 into 1 by a. You just take use of the further this term and just replace x value in this case as 2j plus 1 by 2j into a, and you get this term, a squared by 3 2j plus 1 by 2j whole square. Yeah. So now write down the Brillouin function formula, bj as a function of a. This is nothing but this, this total form 2j plus 1 by 2j into this argument minus 1 by 2j into the other term. So this is 2j plus 1 2j into your first argument was this 2j, sorry, this is multiplied with this term, so it is 2j by 2j plus 1 into 1 by a into 1 plus a squared by 3, 2j plus 1 by 2j whole square. The second term is minus, what was it, 1 by 2j into the cot this term has to be multiplied, that is 2j by a to 1 plus 1/3 a squared by 4j squared. So by cancelling out few terms, you get 1 by a plus a by 3, 2j plus 1 by 2j whole squared minus 1 by a 1 plus a squared by 12j squared. This is your total Brillouin function. Under the condition is temperature is high and therefore a is going to 0. Okay. Now you can further simplify and get the total value as a by 3 j plus 1 by j. Okay. So you just have to take the use of, expand this term, and then you can ignore the not ignore, but you can simplify these terms and you can get the final value as a by 3 j plus 1 by j. And so your total magnetization average is n g mu b into this Brillouin function value is now mentioned as j plus 1 by j into a by 3. So whatever is left is your n. Now you can just directly use the value of a. Now replace the value of a, which is a equal to j times z, right? And this value is over here, that your a value is j times g mu b b by kt. So replace this and you get m equal to n g squared mu b squared b by kt j into j plus 1. This is your average m for the system using quantum theory of magnetism at high temperature limit. Okay. Now the further thing is very simple, that you have to identify what is the susceptibility in this case, or let's say the magnetic moment in this. So basically we do not need to explicitly take out the susceptibility, or you can do that also. We can just use B equal to mu naught H or mu H, whatever. So if B equal to mu naught H, then just replace B equal to mu naught H, then you get M equal to M by H, because you take this H to the other side, left hand side. So M by H equal to chi M is equal to just N G squared mu B squared mu naught J into J plus 1 by 3 kT. But that is not the point. The main point is that now you can say that your mu J value, that is, you can write down the effective this thing as N, taking out all the constant terms aside, we can write this thing effectively as mu J whole squared, which is the effective moment or effective dipole moment for each atomic dipole in the system under this quantum paramagnetic theory. And just like we initially had written down mj for each atomic dipole, similarly for the dipole moment for each atom in the system is written as mu j effectively, which value is nothing but, you can replace it from here. What is mu j? We represent it as if mu j whole squared is equal to mu b squared j into j plus 1. So mu j is equal to mu b root over j plus 1. So this is your count, that I told you that the effective count is basically the net moment, average moment that you get, divided by your Bohr magneton mu b. It is, sorry, I missed out one g factor. So g is also included in this moment relation. Okay, so g squared should be here. So this is your g times this thing. This is just g times j plus 1 So this is your answer, that the effective count of Bohr magneton present in a paramagnetic system using quantum theory at T tends to infinity, high temperature limit. So let's go back and check. That is the answer that is definitely given. Yeah, so your answer is this part, j root over j plus 1 into g. So with this we finish week 5's assignment. I already finished all the problems. So now if you have any questions, doubts regarding the solution that I had done just now, you can let me know, or if not, then we can finish, because I think already we are.
I have one question, ma'am. Do we have magnets only from angular momentum part? No.
Angular what? I did not understand.
Angular momentum from because in previous question, do we get paramagnetism? That's what my.
No, but in question number 7 we are dealing with paramagnets. In other previous questions we are dealing with diamagnets. So in that part these things do not come.
Question number 6, ma'am.
Question number 6 was asked that materials with spinless charged particles. So
Yes.
without spin you cannot have paramagnetism event, because for that you need an uncompensated magnetic moment, as if you have to have an effective spin for the particle. But in diamagnetism the basic idea is you do not need any spin. That's why diamagnetism is an inherent property of any material. You can take any material that can have diamagnetic property, even if that will be very weak, but that will be present.
Okay. Yes, ma'am. Yes.
So that is why you get to use this whole angular momentum j equal to n plus s, because there is this additional spin factor, na? So you have to take use of that.
Yes.
Okay, so if there are no other questions, then we can finish this class, and we'll meet in the next class regarding the next assignment.